What if the most profound discovery in human history was made, and then deliberately buried? We're not talking about rumors or grainy photos here. We're talking about 24 gigabytes of classified NASA data on an interstellar visitor that, honestly, just defied the laws of physics. Data leaked by a ghost-like hacker group revealing a 26-kilometer-wide object that wasn't just passing through our solar system, but get this, actively navigating it. This is the story of 3I Atlas, what NASA allegedly found and why they never wanted you to see it. Let's delve into the data. Event Horizon Cyber Attack. How does a secret stay buried in the digital age? Well, sometimes it just doesn't. In the dead of night on September 2nd, 2025, a hacker collective calling themselves Event Horizon executed a flawless cyber attack on NASA. They didn't just knock on the door, they dismantled it. By exploiting a zero-day vulnerability in an outdated mission planning module, they bypassed layers of federal firewalls. Security logs, which were later leaked themselves, show a terrifying timeline. At 3:14 a.m. Eastern, initial access was gained. By 3:19, they had escalated their privileges to the highest level. At 3:23, the exfiltration began. In less than 7 minutes, 24 gigabytes of compressed files were siphoned from a secure server containing mission telemetry, internal communications, and top-secret analysis on Object 3Y Atlas. By 3:30, they were gone. The attackers left no signature, no digital fingerprints, only a silent void in the server logs where critical audit trails should have been. The specific target was a data archive tied to the Deep Space Network, containing the most sensitive raw telemetry. NASA's internal cyber forensics team was left with nothing but a clean exit, a ghost in the machine that had walked out with the crown jewels. The manifesto and distribution. A data breach is one thing, but a declaration of war on secrecy is another. Within hours of the hack, a manifesto from Event Horizon appeared on encrypted forums. Their message wasn't a boast, it was a justification. They claimed the breach was a direct response to what they termed unlawful cosmic secrecy, arguing that discoveries of this magnitude belong to humanity, not to a select few government agencies. The manifesto warned that the stolen files contained information so sensitive even senior directors at NASA were allegedly unaware of its full scope. Their language was direct: the world deserves to know what its own scientists have found. To prove their point, they began a strategic distribution campaign. Blurred screenshots and heavily redacted memos were sent to journalists and channels known for covering classified science. They specifically avoided mainstream outlets, opting for platforms that would analyze the data without an institutional filter. This drip feed of information created a groundswell of speculation that legacy media couldn't ignore, forcing the conversation into the open on Event Horizon's terms. Authenticating the documents. How can we be sure these leaks are real? The proof is in the details. The screenshots that flooded encrypted channels are layered with evidence of their origin. Documents are stamped confidential in bold block letters. Metadata tags show a 0314 UTC timestamp, matching the breach window from NASA's own security audit. A mission patch appears in the corner, a stylized comet streaking past a NASA vector, flanked by the code 3I Atlas int. One partially blurred memo lists the object's trajectory with terrifying numbers: hyperbolic V infinity of 26.1 kilometers per second, and an eccentricity, or E, of 6.2. These figures confirm an interstellar origin at a speed that, honestly, just defies simple explanation. Another screenshot shows a status log from the intercept team. Most text is blacked out except for a single phrase: plume anomaly flagged at T plus 11.3 seconds. The documents include FITS file headers for raw imaging data and internal routing codes for JPL's document management system. These are the kinds of mundane technical details that are nearly impossible to fake convincingly. Discovery of 3I Atlas. Before the leak, there was the discovery that started it all. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, or ATLAS survey in Hawaii, logged a new object tearing into the solar system at 130,000 miles per hour. Astronomers flagged it immediately. This was no ordinary comet. The object, soon labeled 3Y Atlas, measured an estimated 26 kilometers across, roughly the size of Manhattan, moving faster than any object ever observed inside the orbit of Jupiter. Veteran survey scientist Dr. Lina Takahashi, a fictional name from the leaked files, was quoted in a log. The track was so steep, the software flagged it as an error. Within hours, observatories from Chile to Arizona confirmed the numbers. The object's incoming speed of over 58 kilometers per second defied the sun's gravitational grip. Its trajectory pointed back toward the constellation Lyra, far from the ecliptic plane where most solar system debris resides. To put its size in perspective, the asteroid that killed the dinosaurs was only about 10 kilometers wide. This was over twice that, and it wasn't from around here. Impossible physics and trajectory. Here is where the data gets terrifying. The trajectory of 3I Atlas was not just interstellar, it was unnatural. Calculations from the Minor Planet Center confirmed by JPL revealed an orbital eccentricity of over 6. For context, most comets from our own Oort cloud barely reach an eccentricity of 1.0. Our first interstellar visitor, Oumuamua, had an eccentricity of 1.2. A value of 6.2 means the object was moving on an almost perfectly straight line at a velocity that gravity could barely alter. But the most damning piece of evidence detailed in the leaked mission logs was a sudden unexplained sideways acceleration on July 18, 2025. It was a course correction. The object wasn't just flying, it was steering. The maneuver required a change in velocity, or delta V, that would have required gigatons of force to achieve on an object of this mass. All natural explanations, outgassing, solar radiation pressure, even a gravitational assist from an unknown planet, were systematically modeled and ruled out by JPL's top analysts. The physics simply didn't work unless the push came from within. Surface anomalies, the armor problem. What does a 26-kilometer object from another star system look like? The first leaked images from the Intercept mission were paradigm-shattering. 3I Atlas's surface resembled no comet on file. Imaging analysts flagged a pattern of smooth, almost metallic-looking plating, broken by lines that ran too straight to be natural fractures. One analyst, quoted in a redacted chat log, called it the radiator problem, referring to a gridwork of raised ridges spaced like the cooling fins on spacecraft. These ribs cast long, uniform shadows, and their regularity caused the anomaly detection software to flag the pattern as artificial. Comparisons to known comets like Halley or 67P Churyumov-Gerasimenko fell apart. Their surfaces are jagged and chaotic. 3I Atlas, in contrast, had long stretches that reflected sunlight like polished alloy. Further spectral analysis of this reflected light showed an albedo inconsistent with any known meteoritic iron, lacking the usual chondritic features. It was too smooth, too reflective, and far too structured. Thermal signatures and heat pulses. This is where the data points directly to active technology. Martin Cordner's team at Goddard Space Flight Center, a name appearing in the leak, got a full infrared spectrum of 3I Atlas. The data was so sensitive it was sealed within hours under a restricted embargo. The logs show the Webb telescope's infrared array recorded heat vents pulsing with the regularity of a clock every 90 seconds. Heat would pool along the radiator seams and then burst outward in tight directed jets, not the broad, chaotic outgassing of a comet. The mission logs label this a directive motion event, a term usually reserved for spacecraft thrusters. More disturbing, trajectory analysts correlated these thermal pulses with the object's subtle course corrections. Each 90-second heat pulse matched a tiny, precise adjustment needed to maintain its hyperbolic escape route. The focused nature of these thermal events implies the existence of engineered nozzles or vents, as a natural body's heat would dissipate uniformly across its surface according to the laws of thermodynamics. This was controlled, focused, and undeniably artificial. Chemical composition mysteries. The mystery only deepens when you look at what 3I Atlas was made of. Martin Cordner's team at Goddard was the first to get a full spectrum after the Intercept, and the results were an instant red flag. The early spectra lit up with incredibly sharp, bright lines of nickel. In cosmic bodies, nickel almost always rides shotgun with iron. Yet in every single frame of data from 3I Atlas, iron was almost completely absent. Its signature spectral lines were missing. This isn't just rare. In the entire catalog of known comets and asteroids, it's unheard of. The natural formation processes that create asteroids from protoplanetary disks simply don't separate these two elements with such purity. Leaked notes suggest the isotopic ratio of the nickel was also wrong, indicating it wasn't formed in a typical supernova. The purity level was estimated to be over 99.8%. a level that on Earth requires an advanced electrochemical process known as the Mond process. Radio echoes and communication patterns. Did we ever try to listen? According to the leaked files, yes. And what we heard was terrifying. While public-facing projects might report silence, the classified logs from the Deep Space Network told a different story. Radio astronomers reviewing the intercept mission's raw data flagged a pattern that shouldn't have been there, faint, repeating echoes bouncing back from the object at regular intervals. These were not natural radio bursts or cosmic static. They were precise, clipped signals echoing at intervals that mapped almost perfectly to the 90-second timing of the object's thermal pulses. A veteran telemetry specialist named Marissa Singh, in a chat log later leaked by Event Horizon, wrote, "It's like someone is pinging the probe and it's answering. The pattern is too tight for random noise." The return signal wasn't a simple reflection. It was modulated, carrying a complex phase shift. It was, for all intents and purposes, a reply. This suggested the object was not just passive, but an active system processing and responding to incoming stimuli. Expert analysis and propulsion theory. You can't discuss these anomalies without bringing in a voice of scientific courage like Avi Loeb. The Harvard astrophysicist, who famously staked his reputation on Oumuamua being alien technology, wasted no time weighing in on the 3I Atlas files. He argued the intercepted telemetry read like a blueprint for an advanced propulsion system. Each 90-second heat pulse and corresponding course correction was perfectly consistent with a massive ion drive or a similar engine. In Loeb's words, if you wanted to navigate through a solar system while managing heat and energy, you would use timed, directional thrust. That is what the data shows. But the most jarring evidence was a fragment recovered by the interceptor's dust collector. A leaked lab memo described a fleck of material with a lattice of silicon and doped phosphorus, arranged in layers spaced at micron intervals. The structure was noted as being radiation-hardened to a degree far beyond current human capability, suggesting it was built for long-duration travel through the harsh interstellar medium. This wasn't just a circuit, it was an artifact from a civilization far beyond our own. So, what does this all mean? We have a fictional but detailed account of an interstellar object, 3I Atlas, discovered in 2025, and we have a leaked cache of alleged NASA documents that point to a disturbing conclusion, that the object was a piece of technology. Metallic armor, rhythmic heat pulses that act as thrusters, refined nickel, and structured radio echoes all point to an artificial origin. The most shocking piece of evidence, a microscopic fragment that resembles a computer chip, pushes this story from science fiction into something far more unsettling. While the leak itself is part of this narrative, it forces us to ask a terrifying question. What if our first definitive contact isn't a message but a 26-kilometer machine flying silently past our window? The truth is still out there. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the secrets of science and technology. Thanks for watching Future Fact. After 46 years of exploration, Voyager 1 has finally broken through the ultimate barrier, the heliosphere, and entered true interstellar space. But, the data streaming back from 15 billion miles away is completely rewriting everything scientists thought they knew about the void between stars. This isn't the empty darkness we expected. The space beyond our solar system's protective bubble is alive with invisible forces, mysterious structures, and phenomena that challenge our understanding of the galaxy itself. Today, we're exploring 10 groundbreaking discoveries that prove interstellar space is nothing like we imagined. The magnetic field mystery. The first shock hit scientists when Voyager 1's magnetometer detected something completely unexpected in 2012. Instead of finding chaotic, randomly oriented magnetic fields, the spacecraft discovered that interstellar space has a surprisingly organized magnetic structure. Dr. Leonard Berlanga, from NASA's Goddard Space Flight Center, was among the first to analyze these readings, revealing that the interstellar magnetic field runs nearly perpendicular to our solar system's magnetic field. This sharp 90-degree misalignment suggests we're encountering the edge of a massive galactic magnetic domain. The implications are staggering. These aren't local phenomena but galaxy-wide structures that could influence star formation, cosmic ray propagation, and even the evolution of planetary systems. The magnetic field strength measured at 0.4 nanotesla is actually stronger than predicted, indicating that interstellar space contains more organized energy than our models suggested. This discovery fundamentally changes how we understand magnetic field interactions on galactic scales. The cosmic ray bombardment. Crossing the heliopause in August 2012, Voyager 1 immediately encountered a radiation environment that defied all expectations. Dr. Edward Stone, the mission's project scientist since 1977, watched in amazement as cosmic ray levels spiked by 300% almost instantly. These high-energy particles, accelerated by distant supernova and black holes, bombard everything in interstellar space at intensities that would be lethal to unprotected astronauts. The cosmic ray subsystem aboard Voyager detected particles with energies exceeding 100 million electron volts, radiation levels so intense they would fry electronic equipment within months. But here's the most surprising part. The cosmic ray patterns aren't random. Voyager's instruments have measured systematic variations that suggest interstellar space has natural radiation corridors and safe zones. These findings prove our sun's heliosphere acts as a far more effective cosmic ray shield than anyone realized, protecting Earth and our entire solar system from this invisible galactic storm. The plasma wave discovery. Silence doesn't exist in interstellar space. Voyager 1's plasma wave subsystem, designed by Dr. Donald Gurnett at the University of Iowa, has been detecting constant low-frequency oscillations since entering the interstellar medium. These aren't random static, they're organized plasma waves that create what scientists now call the interstellar hum. Operating at frequencies between 2 and 3 kHz, these waves indicate that interstellar space is filled with electrically charged particles constantly in motion. Dr. Stella Acker, a Cornell University researcher, recently analyzed 5 years of this data and discovered that these plasma oscillations change frequency as Voyager moves through different regions. The waves intensify near density boundaries and quiet down in more uniform areas, creating an acoustic map of interstellar structure. This discovery proves that interstellar space isn't a void, but an active medium where plasma waves propagate across vast distances, potentially carrying information about distant stellar explosions, magnetic field reconnections, and other galactic events happening light-years away. The local interstellar cloud. Voyager 1 isn't just floating through empty space, it's actually swimming through what astronomers call the local interstellar cloud. Dr. Priscilla Frisch from the University of Chicago has spent decades studying this region, and Voyager's direct measurements have confirmed her theoretical models. This interstellar cloud extends roughly 30 light-years in all directions around our solar system, and contains about 0.3 atoms per cubic centimeter, which is incredibly sparse by Earth standards but still significantly denser than the cosmic void beyond. The cloud formed approximately 4 to 5 million years ago when multiple supernova explosions carved out a cavity in the interstellar medium. Voyager's instruments have detected the cloud's temperature at around 6,000 Kelvin, and confirmed it's moving relative to our solar system at 26 kilometers per second. As we drift through this cloud over the next 50,000 years, it'll gradually affect Earth's climate by modulating the cosmic ray flux that reaches our planet, potentially influencing cloud formation and atmospheric chemistry in subtle but measurable ways. The heliosphere's true shape. Everything we thought we knew about our solar system's protective bubble was, well, wrong. Voyager 1's journey has revealed that the heliosphere isn't the neat comet-shaped structure you might remember from textbooks. Dr. Merav Ofer from Boston University has been leading research using Voyager data, and her team discovered that our solar system's boundary is far more complex and turbulent than anyone predicted. The heliopause, that's the boundary between the solar wind and interstellar medium, varies dramatically in different directions. While Voyager 1 crossed this boundary at 121 astronomical units from the Sun, Voyager 2 encountered it at 119 AU, but in a completely different region with its own distinct characteristics. NASA's New Horizons spacecraft, still approaching this boundary, is providing even more data points that suggest the heliosphere might have a more irregular, possibly even fragmented structure. This discovery has profound implications for cosmic ray shielding and helps explain why the interstellar medium penetrates more deeply into our solar system than models predicted, creating these complex interaction zones where solar and interstellar forces are constantly battling for dominance. The density fluctuations. Interstellar space actually has weather, and Voyager 1 is our very first weather station beyond the solar system. Since 2013, the spacecraft's plasma wave instrument has detected at least 5 distinct density variations in the interstellar medium, each representing a different climate zone in deep space. Dr. Bill Kurth from the University of Iowa analyzed these fluctuations and found that interstellar plasma density can change by factors of 2 to 3 over relatively short distances. The most dramatic shift happened in 2014, when Voyager encountered a density spike that lasted several months, indicating passage through a compressed region possibly created by stellar winds from nearby stars. These variations aren't just random, they actually follow patterns that suggest interstellar space has structure on multiple scales. Some regions are compressed by shock waves from ancient supernovae, while others are rarefied cavities carved out by stellar winds. Voyager's measurements reveal that our local interstellar cloud has internal boundaries and substructures, making interstellar space far more dynamic and organized than the uniform medium astronomers once envisioned. The galactic coordinates. Every measurement Voyager 1 takes is helping scientists build humanity's first three-dimensional map of interstellar space. Dr. Nathan Schwadron from the University of New Hampshire leads the team creating these galactic coordinate systems using Voyager's position as a fixed reference point about 15 billion miles from Earth. The spacecraft's current trajectory takes it toward the constellation Ophiuchus, where it will continue for thousands of years unless it's deflected by gravitational encounters. But Voyager isn't just traveling in a straight line, it's mapping magnetic field orientations, plasma densities, and cosmic ray gradients that, vary by galactic location. These measurements reveal that interstellar space has preferred directions and asymmetrical structures aligned with our galaxy's rotation. The magnetic field Voyager measures points toward the galactic center in some regions and away in others, suggesting complex field line geometries shaped by stellar formation and supernova events over millions of years. This galactic GPS system will eventually guide future interstellar missions, helping them navigate the invisible currents and radiation zones that Voyager is now charting for the first time. The temperature paradox. Interstellar space is simultaneously scorching hot and freezing cold, and Voyager 1 has measured both extremes. The interstellar medium itself reaches temperatures of 50,000 to 100,000 Kelvin, hot enough to vaporize any known material. Yet, Voyager's instruments register near absolute zero temperatures because the particle density is so low that there's virtually no heat transfer. Dr. Gary Zank from the University of Alabama explains this paradox. Individual plasma particles move at tremendous speeds, which means high temperature, but they're so spread out that the spacecraft actually experiences the cold of deep space. Voyager's cosmic ray subsystem has detected temperature variations in different regions of interstellar space, with some areas reaching 200,000 Kelvin, where shock waves from stellar explosions have compressed and heated the plasma. These temperature measurements reveal the energy budget of interstellar space, showing how supernova explosions, stellar winds, and galactic rotation, pump energy into the interstellar medium. Understanding these thermal processes is crucial for predicting how interstellar gas eventually collapses to form new stars and planetary systems. The communication miracle. Keeping Voyager 1 alive and transmitting from interstellar space represents honestly one of NASA's greatest technical achievements. Suzanne Dodd, Voyager project manager at JPL, oversees a mission using 1970s technology to communicate across interstellar distances. The spacecraft transmits with just 23 watts of power, less than a refrigerator light bulb. Yet NASA's Deep Space Network can still detect its whisper-faint signals after they travel for 22 hours at the speed of light. In late 2023, Voyager suffered a critical computer failure when cosmic radiation corrupted its flight data subsystem. Engineers led by Linda Spilker performed digital surgery across 15 billion miles, reprogramming 1970s computer code to bypass damaged memory sectors. The repair took months because every command required a 44-hour round trip for confirmation. By April 2024, they successfully restored communication with all 4 active science instruments. This remarkable resurrection really proves that American engineering from the space race era was built to last, giving us precious additional years of interstellar data from humanity's most distant explorer. The Golden Record's journey. Beyond its scientific mission, Voyager 1 carries humanity's greatest time capsule into eternity. The Golden Record, curated by Carl Sagan and Ann Druyan in 1977, contains sounds, music, and images representing Earth's diversity in 55 languages. Dr. Timothy Ferris, who produced the record, selected Bach, Beethoven, Chuck Berry, and traditional music from around the world. NASA engineers designed the record to survive billions of years in space, with instructions engraved in pure gold showing how to play it and how to locate Earth. The record includes greetings from President Jimmy Carter, UN Secretary-General Kurt Waldheim, and children from all around the world. As Voyager travels toward the star Gliese 445, it'll make its closest stellar approach in 40,000 years, passing within 1.6 light-years of this red dwarf. Even after Earth's continents drift beyond recognition and human civilization evolves beyond imagination, the Golden Record will preserve our 1970s snapshot of humanity. Carl Sagan called it a bottle cast into the cosmic ocean, and now that bottle has reached the interstellar sea, carrying our message to whatever intelligence might someday find it drifting among the stars. Voyager 1 has shattered, well, just about every assumption about interstellar space, revealing a cosmic environment that's structured, active, and far more complex than we ever imagined. From magnetic field mysteries to plasma weather systems, this 1970s spacecraft continues revolutionizing our understanding of the galaxy itself. Voyager proves we live in a protected cosmic oasis, shielded from the harsh radiation of deep space. So, which discovery amazed you most? Drop your thoughts below. If you loved exploring these interstellar revelations, hit that like button, share with space enthusiasts, and subscribe to Future Facts for more incredible cosmic discoveries. What if NASA's live feed captured a glimpse of an alien probe, only to cut out at the exact moment it came into view? On June 18th, a single, baffling frame from the feed tracking our third interstellar visitor, 3I Atlas, showed something that looked unnervingly artificial. Then the screen went black. The official story is a network glitch, but the data, verified by citizen archivists worldwide, is real. So what was that razor-sharp edge glinting in the dark? Let's explore this together. The initial discovery. It all starts with a new traveler in our cosmic neighborhood. But this was no ordinary visitor. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a NASA-funded project led by principal investigator Larry Deneau at the University of Hawaii, flagged a new object. This system is our planet's frontline defense, a set of robotic telescopes scanning the entire sky every 24 hours to find asteroids on a collision course with Earth. But this object was different. Its trajectory was hyperbolic, meaning its velocity was so high, it was clearly not bound by the sun's gravity. It was a perfect arc, slingshotting through our solar system on a one-way trip back to the interstellar void. Astronomers globally scrambled to confirm, and within 24 hours, the Minor Planet Center designated it 3Y Atlas, cementing its status as only the third confirmed interstellar object ever detected. The first images revealed the classic fuzzy coma and faint tail of a comet, but its speed and path told a different story. This wasn't one of ours. It was an emissary from deep space, a priceless opportunity for science. The discovery itself was a massive win, a testament to how far our detection capabilities have come since the first interstellar object, Oumuamua, nearly slipped past us unnoticed in 2017. The anomalous frame. Here's where a routine observation becomes a global mystery. The last recorded frame from NASA's feed, time-stamped at 03/17/12 UTC, appears normal at first. You see the dim nucleus of 3I Atlas, its hazy coma, and the faint tail streaking against the black. But then, in the lower left quadrant, something catches the light. It's a glint, but not a soft, natural one. It's a perfectly straight edge. Not a curve, not an arc, but a sharp, geometric line. This is what physicists call specular reflection. Light bouncing off a smooth surface at a definite angle, like light off a mirror. This is in stark contrast to the diffuse reflection from a rough surface like a typical comet, which scatters light in all directions. Independent astronomers, spurred on by the kinds of questions that Harvard researcher Avi Loeb has been asking with his Galileo project about potential technosignatures, ran edge detection algorithms that flagged the anomaly within hours. The software highlighted a line segment measuring roughly 37 pixels, reflecting sunlight at an angle that defied easy explanation. Comet dust scatters light in chaotic, soft ways. This was different. The light bounced cleanly, as if from polished metal, not fractured ice or rock. It was a detail so out of place that it immediately raised an unsettling question. Was this natural, or was it engineered? Data verification. Before anyone could cry cover-up, the question of authenticity had to be settled. Was the image even real? This is where the story takes a fascinating turn, thanks to a global network of citizen archivists. These individuals run automated scripts that constantly monitor and download raw public data feeds from space agencies. Within minutes of the blackout, independent archivists in Australia, Germany, and the United States had already uploaded their captured data packets to public repositories. Each file, stamped with the same 03/1712 UTC timestamp, was secured with a unique SHA-256 checksum. Think of this as a long, unforgeable digital fingerprint for the file. If even a single bit of data were changed, the fingerprint would be completely different. When compared, every single copy matched, bit for bit. The Australian archive's hash matched the German university's mirror and the original NASA relay. There was no evidence of tampering or digital manipulation. This airtight chain of custody proved that the anomalous frame was not a hoax. The data is real, the archive is clean, and the mystery, as the great astronomer and science communicator Carl Sagan would say, is worthy of investigation precisely because the evidence is preserved and verifiable by anyone with an internet connection. Technical explanations. So, if the data is real, could the blackout just be a perfectly timed coincidence? Here's what matters. NASA's live feeds are, well, incredibly complex. They rely on the Deep Space Network, which is this global system of massive radio antennas in Goldstone, California, Madrid, Spain, and Canberra, Australia, all working together to keep constant contact with spacecraft. This network, along with the tracking and data relay satellite system that was first launched way back in 1983, bounces signals from deep space back down to Earth. Dropouts, honestly, are not uncommon. Because the Earth rotates, a probe will eventually set below the horizon for one ground station, and the signal has to be handed off to the next station in the sequence. Sometimes this handover isn't seamless, and you get a brief interruption, what engineers call a handover blank. These usually show up as a 2-second gray screen. Each entry in the Deep Space Network logs, overseen by managers like JPL's Bradford Arnold, almost always provides a reason code like packet loss or relay outage. But the blackout at 0317 UTC, right at the exact moment the anomaly appeared, didn't fit the typical pattern. The public logs showed a gap without the standard explanatory code for a routine handover, making the timing deeply suspicious to many observers. Digital forensics. Let's zoom in on the pixels, because that's where, honestly, the technical debate gets pretty intense. Digital forensics teams immediately analyzed the last frame, and they found two key clues that could offer a mundane explanation. First, the sharp edge of the glint ran perfectly parallel to the borders of several 8x8 pixel blocks. That's a potential fingerprint of the MPEG video compression algorithm. To save bandwidth, these codecs slice frames into a grid, and can sometimes exaggerate or sharpen faint lines, snapping them into these unnaturally straight, blocky outlines. The second clue points to cosmic rays. Space is just filled with high-energy particles that can strike a camera's sensor, leaving a bright white streak that only lasts for a single frame. Digital image experts and university professors like Hani Farid have shown how these single-frame artifacts are actually pretty common in space photography. So one theory is a double hit. A fleeting cosmic ray created a faint streak that was then amplified and sharpened by the video compression, resulting in an illusion of a perfect edge. This provides a plausible, purely technical explanation, but it doesn't entirely close the case since the consistency and brightness of the glint were still considered unusual, even for a compression artifact. 3i Atlas background. To understand the anomaly, you have to understand the object itself. 3i Atlas was already a cosmic outlier before the mysterious frame even appeared. Spectroscopic analysis from the James Webb Space Telescope, detailed in papers by researchers like Martin Cordner at NASA's Goddard Space Flight Center, revealed that it was unusually rich in carbon dioxide. Most comets from our own solar system's Oort cloud, like the famous comet Hale-Bopp seen back in 1997, are primarily driven by water ice sublimating into gas. But 3i Atlas had a carbon dioxide to water ratio of nearly 8:1. This means CO2 was the main engine driving its outgassing and creating its massive coma, which stretched for hundreds of thousands of kilometers. This dense cloud of dust completely obscured the nucleus, making its exact size difficult to pin down, though estimates placed it at under a kilometer in diameter, similar to our second interstellar visitor, 2I Borisov, which was studied in 2019. The Atlas survey's ability to scan the entire sky quickly allowed astronomers to catch it early, providing a rare chance to watch an interstellar comet wake up. This unique chemical makeup already marked it as fundamentally different, a clue that it likely formed in a very different kind of star system than our own. Scientific scrutiny. In science, especially when claims are this extraordinary, the burden of proof is immense. The process of verification is honestly a gauntlet of scrutiny. An anomaly seen in a single frame by a single instrument is just the first step. This principle, that extraordinary claims require extraordinary evidence, is a cornerstone of the scientific method. If one observatory reports a geometric glint, others need to see the same thing, ideally across multiple wavelengths of light, to determine its material composition. Only then does the peer review process even begin. At every stage, scientists are trained to ask, is this a real signal, or is it an artifact? For 3I Atlas, the evidence so far sits on the lowest rung of this ladder. We have one intriguing frame, but no multi-instrument confirmation. Until the Hubble, Webb, or major ground-based scopes produce matching data, most researchers, including veteran SETI Institute astronomer Jill Tarter, would advocate for caution and continued observation, not immediate conclusions. It's a slow, methodical process designed to filter out wishful thinking and avoid the pitfalls of past astronomical misinterpretations, like Percival Lowell's infamous belief in the canals of Mars in the late 1800s. 3 theories. The debate has now fractured into 3 distinct paths. The first is rooted in known physics. Comets are violent, dynamic objects. As 3I Atlas neared the Sun, intense heat could have caused thermal fractures, splitting off a shard of rock or ice. Jets of carbon dioxide erupting from the surface can create torque, making the nucleus spin faster and faster until pieces break off. The glint could simply be sunlight catching the fresh, flat, crystalline face of a newly broken fragment. The second path points to a technical illusion. This is the Occam's razor answer, arguing that the edge is nothing more than a perfect storm, a chance alignment of a cosmic ray, digital compression artifacts, and background noise that tricked our eyes into seeing order in chaos. But the third idea, the one that captures the imagination, persists. This theory, in the vein of speculative ideas from physicists like the late Freeman Dyson, proposes that the edge is exactly what it looks like, something manufactured. A piece of a self-replicating von Neumann probe, a solar sail, or a protective shell designed to withstand interstellar travel. If true, it would mean we're looking at a message or a machine, not a comet. The odds are, honestly, astronomical, but the possibility lingers. Broader implications. An event like this, a potential signal followed by a sudden blackout, ripples far beyond astronomy labs. It triggers a profound shift in public consciousness and even scientific policy. The central question expands from what is that object to who controls the narrative of discovery. It fuels calls for greater transparency, with organizations like the Vera C. Rubin Observatory in Chile being designed specifically to capture and share vast amounts of data openly. For those of us watching, it becomes a powerful test of critical thinking, echoing the public's reaction to the famous 1977 WOW signal. That was a powerful 72-second radio burst detected by astronomer Jerry Amon that remains unexplained to this day. How do you separate a genuine mystery from a technical glitch or a cover-up conspiracy? The timing of the feed cut forces a conversation about our readiness for a potential discovery of this magnitude and whether international protocols like those discussed at the UN's Committee on the Peaceful Uses of Outer Space are sufficient. It blurs the line between healthy skepticism and profound wonder. If a single ambiguous frame can change how we search the skies, what happens when the next visitor leaves no room for doubt? The search continues. So, where does this leave us? The official record states that at 3:17 UTC, the NASA feed for 3I Atlas was interrupted. The final frame contained a geometric glint whose integrity has been verified. The feed drop has been attributed to routine network behavior, yet its timing remains an unnerving coincidence. As of today, there is no conclusive, peer-reviewed evidence to support an artificial origin. But the search is far from over. Missions are already being planned, like the European Space Agency's Comet Interceptor, slated for launch around 2029. It is a brilliant mission designed to lie in wait at a stable Lagrange point in space, ready to travel to a pristine, long-period comet or even a future interstellar visitor for a close-up look. This proactive approach, championed by scientists like the mission's lead, Garant Jones, shows how seriously the scientific community is taking these objects. Every new interstellar visitor is a gift, pushing our technology, our curiosity, and our standards of proof forward. And maybe, just maybe, the next one will provide the answer we're all waiting for. The case of 3I Atlas remains a tantalizing puzzle, perfectly balanced between a mundane technical glitch and a discovery that could redefine humanity's place in the cosmos. The data is real, the anomaly is recorded, but the final explanation is still waiting out there in the dark. What do you think? Was this a ghost in the machine, a natural cosmic coincidence, or our first fleeting glimpse of technology from another star? Let us know your theory in the comments below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our universe. Thanks for watching Future Facts.